Today we're going to be starting the Pre-Calculus 11 course. We're going to be beginning with Chapter 1, Sequences in Series, as you can see on your screen. First, let's talk about some of the big ideas that we're going to cover. At the end of the Chapter 1, the students will understand different types of sequences in series that exist. We can use mathematics to model the patterns of the sequence or the series. By the end of this unit, we will be able to use concrete strategies to determine the pattern that we have. We have an idea of where to start in breaking down a sequence or series. We'll be able to recognize and apply patterns to familiar and unfamiliar situations, make predictions. We will be able to know that a pattern does exist. We will see patterns in life, applications of patterns beyond just the geometric and arithmetic series and sequences. We'll make predictions based on an observed pattern. We'll be able to determine the pattern and identify relevant elements of geometric and arithmetic sequences and series. And we'll also be able to investigate or discover patterns and extend them. So first, we start with section 1.1. That's what we will be doing today. 1.1 is arithmetic sequences. So what we'll do first is we'll define what a sequence is. A sequence is a set of numbers arranged in an order with a first term. We call the first term T1, a second term T2, a third term term 3, and so on. First, let's talk about what a finite sequence is. So a finite sequence simply means that it will stop, essentially. And to give you an example of that, I'll give you two examples actually. So the first example would be 2, 5, 8, 11, 14, for example. So you can clearly see that the pattern has stopped. Another way we can use to represent a pattern that stops, which is a finite sequence, I'll use the same numbers, the same pattern, 2, 5, 8, and then we have some numbers in between, and let's say we end at 101. So on the first pattern, we can clearly see that we have 5 numbers increasing by 3. It stops, it's finite. In the second one, there's some numbers that are unavailable that you don't see. Again, the pattern starts off with 2 and we're adding 5 each time. And then there's some numbers in between and it stops at 101. So these are two examples of a finite sequence, a sequence that stops. And an infinite, you probably heard the number infinite. An infinite number means that it never stops. So it'll continue on forever. For example, 5, 10, 15, 20. And then we use 3 dots to indicate that the pattern is continuing on forever, so it doesn't stop. Let's try a few examples. Example 1, you'll notice that example 1a says complete the following sequences of numbers. So we have 5, 7, 9, blank, blank, 15. So what are the two numbers that we are missing here? And those numbers are 11, 13 are your two unknown numbers that we have here. As you can see. Next, in B, we have 2, 6, so it looks like we're going up by 4, but at further we continue when we look on, we say 4, that's only going to give us 10, and then we're going to get to 14. So that's clearly not going to work. So we say to ourselves, what other types of sequences and patterns we have? Well, that was just trying addition. Let's see if we multiply. So what's 2 times 3? We get 6. 6 times 3 is 18. Times 3 is 54, and 54 times 3 indeed gives us 162. So we've seen that the pattern here is that we're multiplying by 3 each time to get the next number in the sequence. The next one, we have 5, -1, -7. So I think you can clearly see that the difference between each is -6. So we're decreasing by 6 each time. Let's see if that works. So the next one would be -13. And after -13, we would have -19. And we would finish off at -25. And indeed, it does work. Example 1D, we have 80, and then we have -40. And then we have a blank blank, we see 5. So I don't think by subtracting 40 each time we would never end up with a 5. So it looks like we're cutting the number in half and the sign is changing. So essentially we can say we're dividing by -2 or multiplying by -1/2, which is equivalent. So the next number in the sequence would be 20, and then the next one would be -10, and the next one indeed would be 5. So we figured out that the 2 unknowns here are 20 and -10. Then we get to example 1E, and then we see that we have numbers 1, 4, 9, blank, blank, 36. Some people would recognize right away that this looks like perfect squares, and you would be correct. 1 squared is 1, 2 squared is 4, 3 squared is 9. The next number would be 4 squared, which we know is 16. And the next example is 25. Or sorry, the next term is 25. 5 squared. And then we have 6 squared, 36. So the pattern would hold true to that. Next one we have is an interesting pattern. We have 1, 1, 2, 3, blank, blank, 13. So how do we get to the next number in the pattern? So we had 1. We have a second one. Nothing happening there. We have 2, and then we have 3. So if you look closely, if you look at the first term and the second term, if we add the first and second term together, we get the third term. If we add the second and third term, we get the fourth term. So let's try to continue that pattern, and we'll see what that we have there. So we add 2 and 3. That would give us 5. And then we add 3 and 5, that would give us 8. And we add 5 and 8, and that would give us indeed 13. So this is an interesting pattern, and you may see this in the future. And this pattern is called the Fibonacci sequence. So that's example 1. Let's move to page 4, sequences. So a sequence is a set of numbers with some order. Determine the next 3 terms in each of the sequences below. So the next 3 numbers in the first pattern, we can see that we're clearly adding 6 each time. So it would be 27, 33, 39. Adding 6 each time. And I'll put that in the red. The next one is we're multiplying by 2, if you notice. So to get from 5 to 10, we would add 5, but that doesn't work for the next one to get to 20. So 5 times 2 is 10, 10 times 2 is 20, 20 times 2 is 40. So the next terms would be, looking at it, would be 80. 80 times 2 is 160. 160 times 2 is 320. And the next one, again, is that Fibonacci sequence. So we're going to do the next one. So we add the last two terms to get to the next term. The last, yeah, exactly. 21, 21 and 13 is 34. 34 and 21 is 55. So a sequence, just a set of numbers with some order, and we determine the three next terms in each of the sequences below. Next we have an arithmetic sequence. So now we're going to, we're not just talking about sequence, we're talking about arithmetic. So what is an arithmetic sequence? In an arithmetic sequence, the number obtained by subtracting any term from the next is constant. And we could change that if you want wording better, I guess, for what we're going to do a little later on, is I would say subtracting any term from the next term, right? So that means if we have if we're looking for the difference, that would be the fourth term subtract the third term, or the second term subtract the first term. And we call this the common difference. Common difference. Common difference. Let's look at example 2. Determine the common difference for the following sequences. So we have 35, 39, 43, 47. We can clearly see that if you take the last term and you subtract the previous term and you do that for each, the difference is 4. So we say that has a common difference of plus 4. The next one, we're looking for a common difference. We can see that we're subtracting 10 each time. Because 2 subtract 12 would be negative 10. Negative 8 subtract 2 would be negative 10, and so on. So we are going down by 10 to get to the next term, or we're to have a common difference of minus 10, or negative 10. The next one, we're dealing with mixed numbers. So we have 17 and 1/2, 18 and 1/4. So the whole number went up by 1, and the fraction went down by 1/4, because if you take the 1/2 and find the equivalent fraction, it would be 2/4. So we subtract 1/4 from that, so we're subtracting 1/4 to get to 9. So it's adding 1 to the whole, subtracting, which really is adding 3/4 each time. So we're adding 3/4 each time. And the next one has a variable, which is fine. So the next one is we're multiplying, sorry, not multiplying, we're going down by a certain amount. And what is that? Well, the k is there in each term, so we're going to have to use that. So we're going to, it looks like if we put a 3/3 in front of the k, you can clearly see that it's going down by 1/3 k each time. So you're subtracting 1/3 k to get to the next term. So we say that is negative 1/3 k, or negative k over 3. Either one is fine. Negative 1 k over 3. Either one is fine. They're equivalent. All right, so that's going to be the end of the first two examples. In the next video, we're going to continue on with the rest of the section 1.1, arithmetic sequence. We'll see you again soon. Thank you.